Welcome to Advanced Concepts number 6. Today we're going to be discussing the nuclear bomb and comparing the atomic bomb to the hydrogen bomb. My name is Jeannie Moran. What is a nuclear weapon? Well, at the center of every atom, there's a nucleus. By breaking that nucleus apart or combining two nuclei together, it can release large amounts of energy. Nuclear weapons use that energy to create an explosion. Are all nuclear weapons the same? Well, some people think that atomic bombs and hydrogen bombs are virtually the same, and maybe to some extent this is true, because both atomic and hydrogen bombs fall under the heading of nuclear weapons. Nuclear weapons of mass destruction all use nuclear energy to create an explosion. That energy in return is contained in atomic nuclei and released through a series of nuclear reactions and radioactive decay. They each require energy to create an explosion. But there are two ways to make a nuclear weapon. One involves fission, and the other uses fission and another process called fusion. Fission is the splitting of a heavy, unstable nucleus into two lighter nuclei, whereas fusion is the process where two light nuclei come together and release vast amounts of energy. These are two somewhat opposite reactions. The atomic bomb uses fission, and the hydrogen bomb uses three steps. It uses fission, then fusion, and then fission again. During fission, the nuclei of certain heavy atoms split into smaller, lighter nuclei, thus releasing excess energy in the process. This can sometimes occur spontaneously, but also in certain nuclei it can be induced from the outside. A neutron is shot at the nucleus, absorbed, causing instability of that nucleus, and then fission occurs, releasing neutrons which produce an additional fission on at least one other nucleus, which produces more neutrons, and so on exponentially. And when this continues to occur, it can trigger a chain reaction if they're absorbed by nearby atoms and this process continues. When a free neutron hits the nucleus of a fissile atom like uranium-235, the uranium will split into two smaller atoms called fission fragments, giving out energy plus more neutrons which can split with other atoms. When enough atoms have begun to split, the chain reaction needed for a bomb blast has started. Fission can be self-sustaining since it produces more neutrons with the speed required to cause new fissions. This creates a chain reaction. For nuclear bombs, the percent of fissile material needed has to be 80 or 90%, which might be around 50 kilograms of enriched uranium. This will be enough to create the critical mass. 2 to 3 neutrons are produced for every fission. Not all of them are available for continuing the fission reaction. If the neutrons are lost at a faster rate than they're formed by fission, the chain reaction won't be self-sustaining. And here is a little visual that I found on the internet which illustrates the process of one neutron hitting the uranium-235 and in turn producing 3 more. These 3 neutrons, if they encounter other uranium-235 atoms, can initiate more fissions and produce additional neutrons. And again, this continuing cascade of nuclear fissions is referred to as a chain reaction. Let's talk more about the chain reaction. Inside of the bomb, a certain reaction must occur to get to the explosion. This chain reaction involves the fission of heavy nuclei. There are several heavy elements capable of such a reaction. Usually, uranium-235 is used in nuclear weapons. Uranium-235 is radioactive. There are other uraniums such as uranium-238 and uranium-234, but only uranium-235 can do the job. In the nucleus of each atom of uranium-235 are 92 protons and 143 neutrons for a total of 235, thus uranium-235. The arrangement of these particles within uranium-235 is unstable, and so the nucleus can disintegrate easily if excited by an outside source. So when a U-235 nucleus absorbs an extra neutron, it will quickly break into two parts. This is a process known as fission. Each time a U-235 nucleus splits, it will release 2 or 3 more neutrons, creating the possibility for a cascade of nuclear fissions called a chain reaction. Now let's explain fusion. Fusion works in reverse, the opposite of fission. When exposed to extremely high temperatures and pressures, some lightweight nuclei can fuse together and form heavier nuclei, releasing energy in the process. Both types of nuclear weapons, atomic and hydrogen, produce large quantities of energy and radiation. Most of the radiation is X-ray, which heats the air to produce a large nuclear fireball. This rapid expansion of the fireball creates a dangerous shock wave. The shock wave can destroy houses and buildings several kilometers away. In addition, the radiation can cause radiation poisoning. Radiation poisoning, which has the potential to cause DNA mutations, resulting in cancer. The nuclear material and dust that has been irradiated and become radioactive is called fallout. Fallout from a nuclear explosion can travel with the wind far distances from where the explosion occurred and remain dangerous for a very long time. So fusion is what comes to mind when we're talking about the hydrogen bomb. The hydrogen bomb is the more advanced version of an atomic bomb. It has a potential to be 1,000 times more powerful than an atomic bomb, causes larger explosions, which means that the shock waves, blast, heat, and radiation all have larger reach than the atomic bomb. Hydrogen bomb's reach should be closer to 5 or 10 miles compared to 1 mile reach of the atomic bomb. So the hydrogen bomb is a nuclear weapon. Basically, it's also called an H-bomb, and it is a 3-stage weapon. It uses fission, fusion, and then fission again. The first stage is called the trigger. Picture the black ball at the top. It's a small plutonium bomb similar to the one dropped on Nagasaki in 1945. The energy release at this stage is mainly due to nuclear fission, because the atoms of plutonium are split. Tritium is often added to the center of the plutonium core to boost the fission explosion with some additional fusion energy. The only importance of this first stage explosion is to irradiate and heat the material in the central column to 100 million degrees Celsius so that the more powerful fusion reaction can be started there. The second stage explosion comes from the nuclear fusion in the central column. The main fusion reaction involves concentrated deuterium and tritium, both heavy isotopes of hydrogen, which become spontaneously available when neutrons from the first stage explosion bombard a solid material called lithium deuteride located in the central column. Once this hydrogen-rich mix becomes heated to 100 million degrees, the deuterium and tritium atoms fuse together and release enormous amounts of energy. This is the H, or thermonuclear part of the bomb. Then comes the third stage. The fusion reaction gives off an incredible burst of extremely powerful neutrons, so powerful that they can split or fission atoms of uranium-238, called depleted uranium, which is impossible at lower energy levels. This third stage more than doubles the power of the explosion and produces most of the radioactive fallout from the weapon. So unlike fission with the atomic bombs, which rely on only nuclear fission and which can achieve explosions equivalent to thousands of tons of TNT, referred to in kilotons, the power of an H-bomb or thermonuclear weapon has no limit, theoretically. By adding more deuterium, and tritium to the second stage, its power is infinite. Most H-bombs are measured in megatons, equivalent to the explosive power of millions of tons of TNT, hundreds of times or even 1,000 times more powerful than a fission bomb. There are 3 main types of ionizing radiation from nuclear fallout. There's alpha, beta, and gamma. All 3 types of radiation contaminate the area where a nuclear explosion occurred. Alpha radiation is the least harmful. Clothing may protect exposed skin, but mucous membranes are still under risk. Beta radiation causes significant damage at a distance of several tens of meters or feet from the radiation source. Among the consequences could be radiation burns and cataracts. Gamma radiation is the worst of all. With its high penetrating power, it permeates the body, causing damage. Some of those illnesses are radiation sickness, cancer, and gene mutations. Only protection from gamma radiation is lead and other certain substances such as concrete.